Alright, so here I have restructured it so that instead of looking at the real numbers, we're looking at rational numbers, right? So this is Dedekind's work on Dedekind's cut, right? How Dedekind's cut works. Alright, so this pairs with a previous look at this. This is actually what Dedekind said. So this, I just changed it from reals to rationals. Okay? So, the rational numbers Q forms a well-arranged domain of one dimension. Totally fine with that. If A is greater than B, B is greater than C, then A is greater than C. Thus, B lies between A and C. Okay, no problem with that. 2. If A and C are any two different rational numbers, there are infinitely many rational numbers B between A and C. Okay, no problem with that. If A is a definite number, then all numbers in Q are split into two groups, U1 and U2, each of which contains infinitely many numbers. U1 contains those rational numbers less than A, while U2 contains those rational numbers greater than A. A itself may be assigned to either U1 or U2, rendering it either the minimum of U2 or the maximum of U1. Regardless, every rational number in U1 is less than every rational number in U2. Alright? Note that every number in U1 and U2 is rational by definition, since U1 and U2 are parts of the irrational numbers. This means that there are no irrational numbers contained in U1 or U2. This detail is important. For brevity and concern for the reader, proofs are not included. No, this is still a dumb move. Apart from this, the irrationals are also continuous. No, at best this is still a postulate. At worst, it's a baseless axiom. Either way, you're not telling me which one you intend it to be. So, no. I mean, if you're going to say that this is our postulate, okay. Now 4. If the irrationals are divided into U1 and U2, and there exists only one rational number A, which can make this separation, notice before, up here, A wasn't rational, necessarily. It could be anything. So we've kind of moved the goalpost here, right? And this occurs in the original as well, I do believe. Up here, A is a definite number. Oh no, he didn't do that. He was being, okay. He was being deliberately vague. Okay. Then there exists only one rational number which could make this separation. Okay, so obviously this is stupid. If A is 1/2, and that's the maximum of U1, then the cut occurs on the positive side of 1/2. But if it's the minimum of U2, then the cut occurs on the negative side of 1/2. And the eagle-eyed among you might notice, those are two completely fucking different things. They're different sides of a value. Those are different from each other. Notice that Dedekind is building up an argument that pushes all of those values together. This is going to become important, and I've talked about this in the past, but it's actually built into the way Dedekind is doing this. Okay, so now we get to the proof. Still, no. For this first part, given the cut between U1 and U2, A is the perfectly definite rational number which produces this cut. A could be either of two numbers, so this remains among the most ridiculous things I've ever read. It cannot be perfectly definite because it can be any of two. Okay? If B is any number different from A, there are always infinitely many rational numbers C between A and B. Okay, no. We can clearly see that B could be irrational. Okay? Because here, the way we've set it up, we know that there's gaps between the rational numbers. B could be irrational, and it could be so close to A that no rationals fall between A and B. So the stated claim only works if B is rational, just like A and C. And this is why Dedekind's failure to specify that B is real in the original proof is a problem. Because B It could be some non-real number which exists infinitesimally close to A, invalidating the whole thing. Right? This is Dedekind was using circular logic. He's assuming that there's no gaps, and then using that assumption to prove that there's no gaps. And the way that he does that involves your perfectly definite numbers being smudges of infinitely many values that are infinitesimally close. But we'll get to that. Okay. So these next parts, meh. If B less than A, C less than A, C in U1, so B is in U1. Okay. So if B is rational, and I should have noted it before if B was real, right, in the previous one. And this is fine, but it's irrelevant. Flip the inequalities, same thing. Thus, if B isn't A, then B is in U1 or U2. Again, so fucking what? But only if B is rational, right? I already covered the base that if B is irrational, it can't fall in there by definition, because U1 and U2 only contain rationals, right? So if B is irrational, this isn't even true, right? These aren't true. B has to be rational. Okay. So again, and these are like really these should be I shouldn't be okay with these. All right. So this A is either the smallest number in U2 or the largest in U1. Okay. Now this part I have no problem with, but it's also completely fucking irrelevant. Okay. Now here's the crux of the thing. So A is the unique value which can separate Q, the irrationals, into U1 and U2. No. So A can be either of two rational numbers. If the maximum of U1 is a half, for instance, then U2's minimum is some rational that is infinitesimally larger than, but distinct from, 1/2. If we hold U1 and U2 constant, given this constraint here, this means that A can be either of these values. It can be 1/2, or it can be infinitesimally larger than 1/2. Okay? And conversely, we could go the other way. Say 1/2 is U2's minimum. That means that U1's maximum is infinitesimally smaller than 1/2. It's some rational that's infinitesimally smaller than 1/2. Okay? Now A can be either of those two values. Right? So already, given this basic condition, A can be any of three values. Right? Okay, so in asserting that they're the same unique number, we are violating the aforementioned assertion that A is definite, because now A refers to multiple distinct numbers simultaneously and imposes a naming convention which obfuscates them into a single number. Further, since both values are rational, we know already that there exist irrationals between them, which means that all of these are just included as part of the perfectly definite unique rational number A. So A is unambiguously an infinitesimal smudge of many different numbers, and only rendered quote-unquote unique in the way we're establishing our naming convention. That is, every rational number necessarily includes not only the central rational that we think it refers to, but also its nearest rational neighbors on both sides, and all of the irrationals and whatever else which falls between them. Dedekind's original proof did the exact same thing, since we just replaced reals with rationals. So Dedekind originally did the same thing with reals. Okay. What he did is he took what he's calling a definite, what is he calling it? I mean, it was in German, so he didn't call it this. He's calling a perfectly definite number. Or up here, a definite number. Or somewhere else he uses its unique. Anyway, yeah. It's not. He's lying. He's playing word games with you, right? What he's saying is a unique definite number is something that you can uniquely codify in decimal notation, right? So 0.9 repeating forever. That's one real value, okay? But that actually indicates an infinite number of infinitesimally different values. Okay? That is actually what Dedekind has achieved here. And insofar as that goes, if we were honest about it, if we were honest that that's what's happened, I would be okay with that. But we're not honest about what happened, and Dedekind wasn't honest about what's happening here. Right? So this proof of continuity makes exactly the same amount of sense over the rationals as it did over the reals. None whatsoever. Right? The main difference is that we already know of things which exist in the gaps between rationals. So nobody would attempt to prove that the rationals are continuous at this point in time, let alone in this utterly absurd way. But this highlights the fact that it was never a legitimate proof of continuity at all. Okay. Yeah, I don't even know what to say about this. This is just... I don't understand how this... This is like a pillar of modern mathematics, and it's just ludicrous. Jeez.